Okay, so finally, problem 6. Now, this problem is, I would say, this has got to be harder than anything that's going to be on the test. If we give you something like this on the test, then Mr. Rose must have just woken up in a very foul mood. So we have two stars of equal mass orbiting each other in circular orbits. Well, actually, part A is, I'm sorry, I take it back. Part B is the one that's really hard. Part A is very reasonable. So we have two stars orbiting each other, as shown in the picture. The distance between them is d, and so we want to find the angular velocity. So what you have is the two stars are, of course, attracted to each other through gravitation. And there we go. And so the gravitational force between them is just going to be equal to, what did I say? I said the distance between them was capital D. So the gravitational force is going to be g times the mass of one times the mass of the other over d squared. And that is what is going to provide your centripetal acceleration. So these guys are going in a circle with a radius of d over 2. Okay, so, right, so the radius of the circle is d over 2, so they need some centripetal acceleration, and centripetal acceleration is v squared over the radius of a circle, or, easier in this case, because we had to find angular velocity, omega squared times r. And in this case, that's going to be omega squared times d over 2. So the centripetal force here is going to be mass of the star that's orbiting in a circle, right? Times omega squared times the radius of a circle, which is d over 2. And that is your centripetal force. Okay, so now, why not change colors again, because I feel like it. We can cancel an m, and then the d's will group up. We want to solve for omega squared, right? So I'm going to take omega squared equals 2 big G big M over d cubed, it would appear. Okay, so that there, actually that's not quite the answer, sorry, because angular velocity I did ask for, so find angular velocity equals square root of 2 big G big M over d cubed. Okay, so that is part A, and that is something, something like that, something like the binary star problem is something you could expect to see on the test. Fine. Now, the part you could not expect to see on the test is the second part of this, and that is find the spots where you could place a mass such that it would orbit the center mass of the system with the same angular velocity as these two binary stars. So, that may sound kind of strange to you right now. So let me see if I can help with that. These guys go in a circle, right? Okay, well, close enough. Okay, with a diameter of d, they orbit around the center of mass of the system. So let's say they're going counterclockwise. Okay. And they're traveling at omega. And remember, omega squared was 2 big G big M over d cubed, where d was the distance between them. So d is from there to there, and omega is your rate of your angular velocity. So the question is, where can you put something, like a space station or something, so that it would orbit the center mass with the same omega. Okay, so there are 5 such points in the system. One is the center mass, because kind of obviously it's not going to orbit there at all. It's just going to sit there at the center mass. It's going to be evenly pulled on by both stars, and so it would therefore, in a sense, it would orbit with the same angular velocity. It would just have a radius of 0, right? So that's kind of a trivial one. That's the one we can ignore. Now let me show you, there are, I said 2 more are on the axis that runs through the 2 stars. So what I'm saying is, if you extend this axis out this way, there's one out here somewhere, and there's one, by symmetry, you can see there must be one on the opposite side, right? So this here, I'm going to say the distance from here to here is little r, okay? So you've got to place your mass, little m, there, and the combined gravitational pull of the two stars, so I'm going to just label these stars 1 and 2. So 1 is going to exert a force on your m, 2 is going to exert a force on your m, and the net force on these guys, so the total force exerted by both stars, 1 and 2, has to be enough to make you orbit, to make little m orbit with the same omega. Okay, so that's got to equal the centripetal acceleration you'd require would be omega squared times little r. Remember, little r is the radius of the circular orbit of this little green dot, okay? And then omega squared has to be this omega too. And then it's got to, you got to work the mass of the station in, right? To get centripetal force. So what you would do then is, and now we're starting to get really ugly, okay? But the force that one exerts, so this is 1 here, remember, the force that one exerts in the station would be big G times mass of the star, okay, mass of star 1, times mass of the space station, over, and then what's the distance from the space station to star 1? Well, it's, whatever, little r plus d over 2 squared, okay? I mean, that's how you get your force. That's not meant to be anything. That's not a negative sign there, so don't, it's part of the axis, okay? And then for force 2, it's the same, okay, because that's the same mass, or star 2 has the same mass as star 1, except now the distance is r minus d over 2 squared, okay? And that's going to equal, and then you take your little m, or let me back up and say, we can take this, let's see, what's a good color now? How about purple? Ooh, sort of lavender color. Oh my. Okay, so we can take this omega squared here and substitute in this, right? So now we can say, we can substitute this in and get 2 big G, big M, over d cubed, and remember this is also times little m, okay, because now it's this little m here, and little r. And so what's going to happen here is now you can take, wow, that's ugly, okay, doesn't matter really. Okay, so what you can do now is you can cancel, and what you'll get is 1 over r plus d over 2 squared plus 1 over r minus d over 2 squared equals, and then we also cancel, so now we got 2r over d cubed. Okay, now to solve this, this is not pretty, but it's doable. It turns into what's called a quintic equation. So this is a quintic equation in little r, and we're trying to solve for little r. Quintic, you may recognize quint as being either Greek or Roman prefix for 5, and a quintic equation is a polynomial equation that goes up to the 5th power. So a quintic equation will literally be blah 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 times r to the 5th plus blah 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 times r to the 4th plus da 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 da, and then all the way down to, you know, all the powers of r, and then equals 0. So the solution to this, there is no easy rational solution. The solution, if you plug it into your calculator and graph it and have it look for zeros, the solution here will be, I think r equals, let's see, I think it'll be, it'll be r is approximately equal to 1.2 times capital D. So yeah, so it'll be somewhere, you know, out here-ish, and then of course on the other side it'll also work as well. So that takes care of 2 of your 3 points. So these are called Lagrange points, by the way. So let me just see if I can do this again. And here is the center of mass of the system. Here is one star. Here is the other star. And then here is 1 point for your station. Here's another point for your station. The third one I sort of gave you at the beginning, which was the center of the system. And the other 2 points, believe it or not, they're not on the x-axis, but they're actually easier to find. So let me just lead you through that now and say, look, suppose, we can argue from symmetry here. So that was the x-axis I just drew. Here's the y-axis. We can argue from symmetry that if they're not on the x-axis, then they must mirror each other. So if we have 1 point up here, say, then the other one must be down here, because of the symmetry of the system. But the system is also symmetric horizontally, right? So if you have one here, it must be over here as well, which means you would have to have all 4 of these. But I told you now, because the symmetry, right? You have vertical symmetry and horizontal symmetry to the system. So any solution you get must be symmetric, and there must be 4 of them, unless, because we don't have 4 more solutions. I told you there were only 2 more. So where they have to be is actually on the y-axis. Hi.
Hi.
My wife is coming home. Fortunately, I don't really care much about this problem for you because this is, like I said, this is too hard. But they have to be on the y-axis. And so if you solve for this, what you will find, I would honestly rather spend time with my wife and our 2 very, very cute kitties who've been bugging me to play than talking to you about a problem that is way too hard to appear on the test. So I will just tell you that if you solve for this, and you can solve for this analytically, actually, it's a lot better than the other one, you'll get r equals √3 over 2 times d. And so what that means actually is, although I've drawn it horribly here, that the last 2 points are the vertices of equilateral triangles with the m's as the other 2 vertices, or the big stars. So there you go. That's more than you want to know about problem 6. And yes, my wife is already playing with one of the kitties, and the other one's coming over to talk to me. So that is it for me. Good luck on the test tomorrow. And yeah, well, sleep well.